Okay, today we're going to be looking at Unit 16I, and I made a PowerPoint presentation, and it's called Optimization. So, rules for optimization. The idea is to find a value that will maximize or minimize a function. Example 1. What is the maximum product for two numbers whose sum is 20? Step 1. Identify your unknown variables in one variable, 2. Create a function that the question asks you to optimize. Step 3, take the first derivative, set it equal to 0, and solve. Step 4, plug this into the second derivative to show a max or a min. And step 5, enter this value into the function for the optimal value. Once again, you're just creating a function and looking for the max or the min. We know to take the first derivative, set it equal to 0. That's how we're going to find it. What is the maximum product for two numbers whose sum is 20? First, identify your unknowns in one variable. Well, the first number is going to be x, and the second number, therefore, is going to be 20 minus x. Step 2, create a function that the question asks you to optimize. Well, we're looking to maximize the product, so the product is x times 20 minus x, which equals 20x minus x squared. We know this is a parabola with a frown because the negative in front of the x squared, so we know there's going to be a maximum. Step 3, take the first derivative, set equal to 0, and solve. I took the first derivative, set it equal to 0, x equals 10. Step 4, plug this number into the second derivative to show it's a max or a min. So questions might ask you to minimize something, many of them ask you to maximize. Because the second derivative is always negative, we know there's going to be like a maximum. At any point, specifically, x minus 10 is a max. Step 5, enter this value into the function for the optimal value. The product at 10 is 10 times 10, which is 100. The maximum product is 100, which should lead you to think about the fact that the maximum area for a rectangle is a square. Think about that. Question number 2. Sorry, let me move my face down. You are a farmer who is building a rectangular enclosure against the wall of your barn. Draw a picture in your notebook. You have 200 meters of fence. What are the dimensions of the enclosure that will maximize the area? I'm going to quickly draw the picture in your sketch pad. Scroll this up. So it looks something like this. Here's your barn, and here is your rectangular enclosure. And the idea is this is x, and the remaining fence is 200 minus 2x, and you're asked to maximize this area. Oops, let's get back to the presentation. So identify your unknowns in one variable. The enclosure has 3 sides, 2 of which are congruent, and the remaining side is 200. Number 2, create a function that the question asks you to optimize. Well, the area is length times width, so it's x times 200 minus 2x, which is 200x minus 4x squared. Did I make a mistake? Yes, I did. Sorry. That's supposed to be a 2. So you'll follow through with me. I apologize because I'm not redoing this. It's 200x minus 2x squared. Okay. Take the first derivative and set it equal to 0. So it's 400 minus 4x. Therefore, x equals 50. Sorry about that. X equals 50. Plug this number into the second derivative to show it's a max or a min. Now, the second derivative is always negative 8, so the area is a maximum at x equals 50. Enter this value into the function for the optimal value. The maximum area is going to be like 50 times 200 minus 2 times 50. 200 minus 100 is 100. 100 times 50 is 5,000. So the volume is 5,000 square meters. Sorry about that. Last problem. You have a piece of cardboard which is 6 meters by 8 meters. You cut out squares from each of the corners, fold up the sides, and create an open box. So what's the visual for that? Let's go back to Geometry Sketchpad. Let's scroll this up a little bit. The idea is you have a big piece of cardboard, right? It's 6 by 8, and you are going to cut out squares and then fold those squares up, fold the sides up, so you have an open box. That's the idea. So the question is, so once again, this was 6, this was 8. The idea is, so the question is, how do we maximize the volume of this open air box? What length should the sides of the square be to maximize the volume of the box? What is the maximum volume of the box? Step 1, identify your unknowns in one variable. So we know that we don't know what we're cutting out here. It's x by x. So we know the height is x. What's left over for the sides? Well, we took out x's on both sides. So it's 6 minus 2x for the length and 8 minus 2x for the width. Sides of the square x. After folding up the sides, which have height x, the base is 6 minus 2x by 8 minus 2x meters. Create a function that the question asks you to optimize. We're trying to optimize the volume. The volume is x times 6 minus 2x times 8 minus 2x, which is 48x minus 28x squared plus 4x cubed. Take the derivative, set it equal to 0. Take the derivative, set equal to 0, and solve. Now, I'm telling you it's a part 2. I looked it up. I thought I could factor it. You can't. Therefore, it would be a part 2 question. So, and you'd know that, I would tell you. So I'm using my GDC. I'm using Desmos, but because it's easier to take pictures. So you can see I plotted the parabola, and the zeros were at 1.131 and 3.535. Step 4, plug these numbers into the second derivative to find the max and the min. So you can see from my Desmos, I had the function was f of x. G of x is the derivative of f of x, and h of x is the derivative of g of x, which means h of x is the second derivative. You can use Desmos to plug the two values into h, and you could see here that h of at 1 point, the second derivative at 1.31 is negative, therefore it's a max. Also, the second derivative at 3.535 is positive, so that's going to be a minimum, theoretical minimum. We'll see that the volume, you could see the volume is actually negative, so it's a theoretical minimum. Okay, let's get back to the presentation. I said the second derivative. Because the second derivative at 1.131 is negative, this will maximize the volume. Enter this value into the function for the optimal value, and we can see that the maximum volume will be 24.3 meters cubed. Now, you're lucky because I think most of the problems you get in the book and on the IB exam, they give you a function. So you don't have to construct the function. You're lucky. Have fun. Exit. Click on this recorder, shut it off. Stop sharing.